called the accumulator. This is an accumulator of physical objects, vehicles, and fuel. And it's perfectly safe because there's no space debris there. Cryogenic propellants, docking for crew cargo and tankers, and crew modules if they have heavy radiation shielding, docking for all your Mars expedition vehicles and payload carriers, which could involve as many as 20 or more separate vehicles, solar arrays to power the way station and multiple depots. You'd also need a lunar polar mining and science base, which implies lunar ferries with landing legs on the ferries. The cargo crew and tanker capsules would go from the lunar surface to L1 and back, or vice versa. Expeditions at a larger scale. For robust lunar and Mars expeditions, thousands of tons, not hundreds of tons, would be required if you're really serious about it. Such masses would need to be launched within a year or two, not a decade or two. The current rocket they're building would take several decades to launch that much, even to low Earth orbit. Frequency of launch is critical to preventing thermal damage to vehicles, especially in low Earth orbit. If launch prices drop by 90% due to reusable vehicles, we can launch these larger masses for the same cost as current programs. Reusing in-space vehicles also reduces launch costs because you don't have to launch the same type of reusable vehicle all over and over again. Mass production of such vehicles with many common components and parts would reduce costs. So, here is a way station at L1, and let me point out some features. These two objects here are propulsion units that are fitted with a depot-like sun shield, and they would be using cryogenic propellant. These are lunar ferries that bring propellants, or they could be bringing equipment from L1 down to the moon. These would probably be bringing lunar propellant from the moon up to L1 to be put into the depots, which are here and here, I guess, right? And maybe these two also. We might need 6 or 7 depots. Each depot would store 200 tons of cryogenic liquid hydrogen and liquid oxygen, but you can take months and months to accumulate this because the fuel is going to stay there. If we can send the whole thing to Mars, it's perfectly safe at L1 too. So we also have all the Mars ferries here, at least the cargo ferries, 7 of them, and sometimes there's one part at the end, 1, 2, 3, 4, 5, 6, so there's one more that's not being shown here. And then now at the end we've got the crew cluster with heavy shielding and these additional modules around the central module where the crew would be, and a crew ferry right there. You can see the rocket engines with the nozzles flush with the base heat shield to protect the engine, internal parts of the engine bay from any rocket exhaust completely. So and then these two objects right here are the large cargo carriers. Each one of these would carry 8 large cargo containers, like it would be on a tractor trailer like this. Each of these is 25 tons. You'd have 8 of them in here and 8 of them in there. So what you're looking at would be able to eventually land as much in the first expedition as 625 tons of cargo, not counting the ferries themselves on the surface of Mars. That's where the efficiency comes in, because you're using the same ferry several times. How do you dock a spaceship? The slowest part of space operation is docking, because you have to go so slowly. Most of the docking systems today have a very narrow docking point. And if something bumps the vehicle, it could break, especially if it's a pressurized docking port, and the people inside could instantly die of depressurization. So I've come up with the concept of a docking disc, which makes the two vehicles flat together over about an 8-meter, or whatever the diameter of the vehicle is, surface, so that and inside there you have a docking system, a latch mechanism, maybe 2 meters in diameter, similar to the one that's used in the Dragon capsule. So that grabs it and pulls it in tight, and then if something bumps one, it's going to basically bump the entire structure, not just break off one vehicle. And then once they're secured and docked, they can be easily loaded and unloaded by robots. Now, I don't know if I showed the robot here. Yeah, there it is. This robot is on rails. See the rails? So the robot can grab stuff out of these. Their door is like a shuttle cargo bay door. Opens up to protect them against thermal shock. Grabs out of there and stuff it into one of those. Because it's all rigid. It's not going to move. It's just like the jig factory concept of things not moving when you're working on them. Let me go back over here. So now you can see some of the docking discs. Here's an 8-meter disc. Like these things are 15 meters, 10 to 15 meters in diameter at the base. They're pretty large. So these might be 8 meters across or so. And then the docking mechanism in the middle is 2 meters across. They're already using similar mechanisms, but they don't have the disc part to protect it mechanically. And at the end, we've got here either a depot or a propulsion unit, and the ones at the top are the lunar carriers. That's in the early stages of delivering propellant to the L1 depot. You might not need that many lunar fuel ferries. Okay, the docking truss with robots. The version of the Canadarm, originally used in the shuttle, is now used in the station. It can move pressurized modules from one berth to another. Similar large robot arms and rails running along the docking truss would move cargo from or inside one vehicle and attach it or place it inside another or even into a temporary warehouse thermal shelter, which could be an empty cargo carrier. So there's a robot arm on the space station, so you get sort of an idea of what they look like. Okay, I call this Hell on Wheels in Space, just like the TV show. You have a rail head. A slightly more complicated version of the Canadarm would be mounted on rails. The robot arm would be deployed with a collapsed docking truss package. It would progressively lay its own rails on the truss as it built the truss and assemble the next truss section as it moves along the track. It would then attach the docking station discs along the truss and connect power cables. It would then be ready for vehicles to dock and for cargo to be moved. So to give an example of how complex this is a track laying system, a complete mechanical system that was being used in 1978. So if we can build something that's this complicated in 1978, where we don't even need a roadbed, because the roadbed is the truss itself, we can surely do this in space where there's no massive forces acting on the system. Now, how does the robot or rail car keep from drifting away? Well, these are the bogies of a roller coaster. If you can see at it, the wheels on top bear the weight of the roller coaster car, and on the side, both sides and the bottom, there are other wheels. The whole assembly is called a bogie, which keeps the car locked onto the track. The same system can be used in space so that the car doesn't float away. So here's a picture of what that might look like running along the track. You can see the track and you can see the truss. The truss is basically about 15 meters or almost 50 feet wide. Gives you a sense of the scale of it here. So this is what this is it provides a fundamental basis for the capability to fabricate larger structures in space that can be launched or assembled. Because the truss can dock vehicles carrying additional building materials, and since the robots can get them and move them to the space construction site and assemble them, structures of almost any size can then be built, limited by the cost of mining and transporting the materials and getting them to wherever the station is, like just asteroidal materials, for example. Docking truss with robots are the basis of future space industries. It's the equivalent of a port and an unloading facility. With the addition of storage facilities, the system becomes a full transshipment site. Since the truss can be extended, it can support construction of a variety of space industrial facilities, including pilot-scale systems. Some of the equipment for such a site could be constructed there, while smaller equipment could be launched from the ground and attached. Trusses in space. Truss in space will not rust. It can be made from a variety of materials. You can use a triangular or rectangular cross-section trusses, and there's a list of all the different ways that you can assemble them. We're going to skip over that. The value of trusses. There's no strong force of gravity, so the space structures don't need to be super heavy, but depending on what they're used for, they connect objects in space together so that nothing is floating loose and could be lost. They're stiff and rigid, which prevents long structures from bending and warping, and they can be very lightweight or very heavy to resist bending and stress from the construction activity itself. The space designers have used concept space and trusses for decades. It's now becoming clear how useful they can be. Here's a picture of the beam builder. I actually touched this beam builder in the beam back about 30 years ago. It was down at the Michoud plant in those days. There's a whole series of that that I'll have in another show on power satellites, I think on Saturday. The Dexter manipulator, it's a new ability. So there's a whole bunch of stuff talking about Dexter, but just there's what it looks like. It has multiple arms, but imagine the Dexter on rails, so it can do a whole bunch of different tasks, including carrying things, assembling things, doing very, very intricate manipulations, and they're now testing it out on the space station. So